Hello everyone, welcome to my channel. For the last decade, electronically controlled motor drives have become vital to automated machinery, from traction and propulsion to servo systems, robotics, and automated machine tools. Developments in digital and power electronics have provided high degrees of control at affordable prices, and with low inertia and wide availability. The AC induction motor is the workhorse of the industrial motor drive industry. But even with simple control needs, further improvements in induction motor performance and efficiency are possible using sophisticated digital control algorithms to handle variations in parameters such as torque and load. This is known that torque can be controlled via flux or currents. In vector control, in our case indirect vector control, the goal we want to achieve is decoupled torque and flux control, like DC machine control. We observe one-phase winning stator and model it with this first-order transfer function, and we use classical PI type for regulation. If the current regulation were done in the coordinate system, The current reference would not be of the Bolens type, but of a sinusoid at some frequency, which would result in a signal delay. The first idea is to solve this problem by increasing the proportional action of the regulator, which would result in an increase in the bandwidth of the system. In this case, even if we had an ideal situation in terms of pro-filter noise and disturbance, the question remains how much the proportional effect can be increased, bearing in mind that no matter how accurate the model, there are always things we have neglected or overlooked. With AC machines at relatively high torques, and a very small phase error can cause major problems, in the sense that the control will no longer be disengaged, that we can no longer independently control torque and flux. For this reason, it is necessary to perform current regulation in an imaginary DQ coordinate system, where our references would really be springboards, and we would not have problems with the phase, because the signals ID and IQ would be constant even in the steady state. Based on the principle of internal model principle using the classic PI controller, we come to the problem of unwanted coupling, where the control variable UD acts not only on ID but also on IQ. For more details on this problem, see our last videos. This problem of axial decoupling can be solved by introducing this cross-integral action in the regulator, or this O-name decoupling technique. Having explained what shape our controller should be, we now need to determine the optimal parameters of the digital controller that we will implement in the computer. For that, we need models of the control object for the three-phase inverter and measuring system in a discrete domain. In the real situation, the voltage calculated as the mean value at the interval of one selection period is applied only in the next period. This will be the discrete transfer function of the control object. The inverter is represented by a simple DC power amplification VDS, which amplifies the pulses of the PWM signal, which in relative units amounts to this. The problem that occurs when measuring the stator components of the current is the following. Phase currents that are otherwise sinusoidal have additional noise at this frequency. As it is clear that the sampling theorem will not be satisfied. For this reason, it is necessary to filter everything over with an analog filter. As we cannot achieve such an ideal filter, a compromise solution is achieved through a combination of a real analog filter and oversampling means the signal from the current sensor is selected more often than the rest of the system. In this way, by fulfilling the modified Shannon theorem means that the amplitudes of the signals at frequencies greater than half the selection frequency are less than the value carried by the bit of the least weight of that ADC converter would obtain acceptable results. With the approximation that the current sigma is a pure sinusoid and that it changes linear during one control period, this will be the transfer function of the measuring system. This is the assumed form of the digital controller transfer function in the form of a classic PI controller. In order to find the optimal values for the controller parameters Kp and Ki, it is necessary to observe the characteristic polynomial, which is the denominator of the transfer function of the whole system. We obtain this after calculating the characteristic polynomial. The algorithm for determining the optimal parameters of the controller is executed by calling certain M-files. To learn how to design such controller, you can see these videos. these functions which evaluate the parameters by searching for the best solution in the desired parameter space. The criterion by which the optimality of the parameters is determined penalizes the following phenomena. Poles on the negative part of the real relaxes with the plane. Poles close to the unit circle z-plane. Amping coefficient less than 0.4. By modifying the criteria, we would get different optimal values for the parameters Kp, Ki, Kc of our regulator. In the next video, we will take a closer look at this model and explain all subsystems.